Thank you, Martin, for the introduction and for the invitation. Thanks to Nagasuma, Chandra, Martin, Lopez-Garcia, Carmen, Molina-Paris, and Saumyadipta, Pyne, sorry for the pronunciation, for organizing this meeting, and to this Center for the Hospitality. Well, I am a mathematician, sorry. So I am going to give an informal talk, but with a few mathematical details. My objective in this talk is to present some work in progress dealing with time-discretized versions of the well-known SIS epidemic model. Well, the talk is closely related to a joint collaboration with Martin Lopez-Garcia from the University of Leeds and one of my collaborators at the Complutense University of Madrid, Maite Rodríguez Bernal. Well, here is the organization of the talk. First of all, in a first session, I present the well-known stochastic SIS epidemic model as a continuous time birth and death process. And I comment on a discrete time version of this model we can find in the literature in terms of a discrete time birth and death process. In the second session, I construct a second discrete time version, the time-discretized version of the stochastic SIS epidemic model. I construct by observing the original epidemic model at a sequence of infection times. In this second session, I comment on two interesting properties of this time-discretized version. The first property is related to the dynamics of the model in the long term, and the second property is related to the random length of an outbreak. Well, the question is that we have two discrete time models in order to approximate a continuous time model. So the question is, what is the best option if we try to approximate the original model by using discrete time models? Well, in order to answer this question, I comment on two descriptors. The first descriptor is associated with, The first descriptor is associated with the probability of missing an outbreak or the no detection of an outbreak. And the second descriptor, which is the key descriptor in our approach, is related to extreme values during an outbreak. While I present a probabilistic criterion by using the Hellinger distance between two probability distributions, and these probability distributions are associated with extreme values during an outbreak in the original model and in the time-discretized version. I finish the talk with a few concluding remarks and comments on the main references. Well, we start with our motivating comments. Well, in the SIS epidemic model, we deal with an homogeneously missing population of n individuals or hosts. Each individual passes from being susceptible to turning infected to becoming again susceptible. So we deal with a very basic model with bidirectional transition between two basic states. The state susceptible, someone who is free of the disease, which is denoted by S, and the state infective, which is denoted by I. Well, in our case, an infective host is someone who is infected, infectious, and may transmit the disease to susceptible individuals. An infective individual is continuously generating contacts, infection contacts with susceptible individuals according to a Poisson process of rate beta during its infectious period. The infectious period of an infective individual is assumed to be an exponentially distributed random variable with a certain intensity, gamma. We also consider an additional flow of external infection according to a Poisson process of rates beta prime. Well, infectious period of infective individuals and Poisson processes associated with contacts between infective individuals and susceptible individuals, or due to the external flow of infection, are mutually independent. This description results in a continuous time birth and death process, when we consider in particular the number of infective hosts at time t. This is a very basic stochastic process. It is defined on a finite number of states, and in this process, birth rates are associated with a new infection due to contacts between susceptible and infective individuals and the flow of external infection. And death rates are associated with the recovery of an infected individual. Well, it is a very, very basic exercise to establish that we may derive an explicit expression for the limiting distribution of the number of infective individuals at time t, where time t tends to infinite. Well, here is the expression. It has a product form at which we are considering birth rates and death rates. This limiting distribution does not depend on the number of initially infective individuals. Well, the end of an outbreak is associated with the first visit to state 0. This means that the random length of an outbreak can be seen as a first passage time to state 0. In other words, the random length of an outbreak can be seen as a continuous phase-type random variable of order n, the total size of the population, and with representation given in terms of a vector of initial probabilities and a rate matrix. The vector of initial probabilities is a null vector with a single one at the position of the number I of initially infective individuals. And the rate matrix consists of those infinitesimal rates associated with transitions from and to states 1, 0, n, states at which the outbreak kicking process. Well, as you can see here in this expression, we deal with a tridiagonal matrix. So it is very easy, for example, by using a Gaussian elimination approach to derive the inverse of this matrix, and as a consequence, we may compute the expected length of an outbreak and other moments by using the inverse of this matrix. Well, by using the infinitesimal dynamics of this continuous time birth and death process, Linda Allen, and Burgin suggest to approximate the continuous time birth and death process by using a discrete time birth and death process. They consider a sequence of random variables for which only 3 possible events can occur: a new infection, the recovery of an infected individual, or no event in an infinitesimal interval of length dt. In particular, a new infection occurs with probability lambda I multiplied by dt. The recovery of an infective individual occurs with probability mu I multiplied by dt, and no event occurs with probability 1 minus lambda I plus mu I multiplied by dt when this value is strictly positive. Well, they suggest to approximate the continuous time birth and death process arising in the SIS epidemic model by using a sequence of time steps. T equals 0, dt, twice dt, 3 times dt, etc. Well, in a graphical way, they are considering this basic discrete-time birth and death process instead of the real situation. In the continuous time birth and death process, when we consider an interval of length tau equals dt, transitions may occur from any initial number of infective individuals to 0, 1, y minus 1, y, y plus 1, n minus 1, n, with one step transition probability matrix, with one step transition probability which is strictly positive. Well, we can look at this model as a very rudimentary process, but this model at a first glance is very rudimentary, but is very good for practical use. Well, the first question to deal with is when can we say that the time step tau equals dt is sufficiently small to have a good approximation of the continuous time birth and death process. But putting aside this question, let me say that regardless of the length of the time step, this model has two basic but very, very interesting properties. The first property is related to the behavior in the long term. The stationary distribution of the discrete time birth and death process of Allen and Burgin and the limiting distribution of our continuous time birth and death process in the SIS epidemic model are identical, regardless of the time step. This means that the influence of the time step becomes negligible when the time, continuous time or discrete time, tends to infinite. The second property is related to the random length of an outbreak. The random length of an outbreak in the continuous time birth and death process is a continuous phase-type random variable. And the random length of an outbreak in the discrete time birth and death process is a discrete phase-type random variable. So we are not considering the same distribution. But the expected length of an outbreak in the SIS epidemic model is equal to a scaled version of the expected length of an outbreak in the discrete time birth and death process of Allen and Burgin, where we are using the time step tau multiplied by the mean number of states before the first visit to the state 0. Well, with all probability, you agree with me that the birth and death process of Allen and Burgin is not the natural way to approximate the continuous time model. Probably the most natural way is to observe the continuous time birth and death process at a sequence of spatial times. Well, we are going to construct this second discrete time version. We call it in what follows the time-discretized version. Well, let us consider an interval of length t prime, 1 year, for example. We decompose the interval into a number m of subintervals of identical length. Okay? For example, 12. And we are considering January, February, March, etc. Or 44. And we are talking about weeks, okay? Well, anyhow, we decompose the interval 0 t prime in a certain number, m, of subintervals of identical length. So we are going to record the number of infected individuals at the end of each interval. We are going to take m spatial times instead of the original continuous time process in the interval 0 t prime, okay? Well, by using this definition, we are dealing with the real description of the original process. So instead of a discrete-time birth and death process, here we are considering a discrete-time Markov chain defined on the same state space, but whose one-state transition probabilities are all strictly positive. So we are considering a more complex process. Well, we have in common a property with the proposal of Allen and Burgin. In our case, the stationary distribution of our time-discretized version and the limiting distribution of a birth and death process, the continuous time birth and death process, are identical. So we have the same property, but with respect to the random length of an outbreak, we don't have the same property. In our case, the random length of an outbreak in the time-discretized process is stochastically larger than the random length of an outbreak in the continuous time birth and death process. As a consequence, the expected length of an outbreak in our time-discretized version is always greater than the random length of an outbreak in the original model. Well, in these figures, I illustrate the ratio between the random length of an outbreak in the original model and the expected length of an outbreak in the time-discretized version. When we consider in particular a population of 12 hosts, at time t, we consider a single infective host, so we deal with an invasion time. We consider that an infected individual recovers after 1 unit of time on the average, and we plot this ratio as a function of the time step tau and as a function on the parameter beta, the rate associated with contacts between susceptible and infective individuals. We consider 3 values, beta prime equals 1, 5, and 10, for the rate associated with external infection flow. Well, the blue color is associated with a ratio with values closer to 0, about approximation. And the color pink or barbell is associated with values closer to 1. So as intuition tells us, we have a good approximation when the time step is smaller, as you can see here. Okay, well, nevertheless, we have to answer the same question. Well, in our case, the length of the interval under consideration, T prime, is equal to the number m of inspection times multiplied by the time step. So we may reformulate the question about the length of the time step in terms of the number of inspection times. The question is how to select the smallest number m of inspection times in order to have a good approximation of the stochastic SIS, stochastic model, when we consider only the number of infective individuals at the sequence of inspection times. This question is closely related to the random idea between the sample path of infective individuals in the original process and the sample path of infective individuals in the time-discretized version. Well, I use here in this figure the blue color for the sample path of infected host in the original SIS epidemic model. And I use the red color for the sample path of infective individuals in the time-discretized version. We are considering an interval 0 T prime and 1, 2, and 3 subintervals. So putting aside the time t equals 0, we are considering 1, 2, and 3 inspection times, and we observe 1, 2, and 1 infective numbers at the first, the second, and the third inspection times. Well, it is possible to prove that the total area between the sample path of infected host in the original and the time-discretized version converge almost surely when the number n of inspection times tends to infinite. Nevertheless, if we try to choose the probability distribution of this random variable in order to determine the smallest number m, well, the question is not very easy. Well, a natural way to select m will be to take the expectation of this random variable and to establish m as the smallest number, such as this expectation is less than a predetermined value with epsilon sufficiently small, for example. But it is not easy. I think that it is impossible to derive an explicit expression for this expectation. Well, in order to suggest an alternative way for the selection of the number m of inspection times, we have considered various probabilistic descriptors. I am going to talk about 2. The first is a successful probabilistic descriptor, and the second one is the K descriptor for us. The first descriptor is the probability of missing an outbreak. Let me say that when we consider 2 inspection times, the continuous time process is evolving between them, and an outbreak may end, and later may another outbreak start again before the next inspection time. So we would like to quantify this question in terms of a probability. In particular, and for a fixed number I of initially infected host, we define the probability delta I of t as the conditional probability that starting from I initially infected host, the sequence of inspection times does not allow to detect the end of an outbreak, provided that an outbreak occurs within the interval 0t prime under consideration. Well, we may derive an expression for this conditional probability in terms of the time-dependent solution of a modified version of our continuous time birth and death process, and in terms of the transient solution of a modified version of a time-discretized version. Well, in both cases, to define these modified versions, we are replacing the state 0 by an absorbing state in order to identify at the interval, at time t prime, that an outbreak has taken place. Well, for this first term, we may derive expressions according to eigenvalues and the solution of a system of linear equations. And for the second term, we may derive expressions by using the powers of the underlying one-stage transition probability matrix. Well, I omit the details. Let me illustrate the behavior of this conditional probability. Well, we are going to consider the same parameters as in our previous figures. And in this case, we are considering the probability of missing an outbreak as a function of the number m of inspection time as a function of the parameter beta and as a function of the parameter beta prime, as we did a few minutes ago with the other figures. Well, in this representation, the black color is associated with values for the probability closer to 0. So in such a case, we are dealing with a good approximation because the probability of missing an outbreak is close to 0. And values closer to 1 are associated with the color yellow and white. Well, let me explain that according to, for example, this case, or this case, or this, we deal with a very good approximation. But the descriptor is problematic. It's problematic because if we consider, for example, this figure, the selection of the value m does not depend on the rate beta, which is surprising. It's surprising because when we deal with an increasing rate beta prime and increasing values of the parameter beta, we are going to have major outbreaks. So it is very problematic if we try to construct a probabilistic criterion for the selection of m in terms of this probability, because the influence of this parameter beta or beta prime or both is not significant. Probably the question, this question can be explained in terms of the probability associated with the conditional probability. The probability of the event we use to define the conditional probability in these cases, in particular in this case, is very small, even negligible. So we have a problem if we are interested in this descriptor. Well, this is not the key descriptor in our approach. The key descriptor in our approach is related to the maximum and minimum variability of the continuous time birth and death process. In what follows, I am going to try to characterize the distribution of the maximum number and the minimum number of infective hosts. And I am going to use this joint probability for the continuous time birth and death process and for the time-discretized version of this model, in order to later to define a probabilistic criterion in terms of the Hellinger distance between both probability distributions. Well, for a fixed number I of initially infected individuals and a predetermined interval of length t prime, we define two random variables. The first corresponds to the minimum number of hosts which are simultaneously infected at any time in of the interval 0 t prime. And the second one corresponds to the maximum number of hosts which are simultaneously infected at any time of the interval 0 t prime. Well, we may characterize the joint distribution of the corresponding random vector by using probabilities qi of y prime, at which we determine the probability that the original process, the continuous time birth and death process, is confined between two values, y and y prime. Of course, when we choose y equals 0, we determine the marginal distribution of the maximum number of infective hosts. And when we choose y prime equals n, we determine the marginal distribution of the minimum number of hosts which are simultaneously infective. For any other value, the computation of this probability can be reduced to the analysis of the transient distribution of an absorbing birth and death process, at which we are considering two absorbing states, y minus 1, y prime plus 1, and other states, y plus 1, etc., and y prime are transient states. Well, here is a representation of the corresponding infinitesimal generator of this absorbing birth and death process by using a 1 and 2 column vectors at which we record infinitesimal rates associated with transitions from this set of transient states to the first absorbing state or to the second absorbing state. This matrix S of y prime is a tridiagonal matrix at which we record infinitesimal rates associated with transitions between states of this class of transient states. Well, this matrix is a submatrix of the original infinitesimal generator of the SIS epidemic model. Well, without going into detail, the key point in the computation of this joint distribution in terms of the probability Qi of y prime is the computation of a matrix exponential, the exponential of the matrix S of y prime. For me, it's a very nice and interesting mathematical problem, but without going into detail, we use, because Martin is one of my collaborators, we use a Cayley-Hamilton approach in order to compute this matrix exponential. Cayley-Hamilton approach allows us to compute the probability in terms of the eigenvalues of the matrix S of y prime, and the solution of a system of linear equations, because we need a set of auxiliary coefficients. These coefficients can be written in terms of the eigenvalues and the powers of the matrix S of y prime. It can be proved that these eigenvalues are all strictly negative real numbers, and it is seen that they can be found in a bounded interval. So for numerical purposes, the situation is very good for computing the corresponding matrix exponential. Well, once we have computed the joint distribution between two random variables, we may derive the mass function of the minimum number and the maximum number of simultaneously infected hosts in the continuous time birth and death process. But in a similar manner, we may compute the joint distribution of the corresponding random variables in the time-discretized version. Well, in the corresponding analysis, the matrix exponential is replaced by the powers of a certain one-step transition probability matrix. The problem is different because instead of a continuous time process, we are dealing with a discrete time process. At the end, we have two discrete distributions, okay? Our proposal is to use the Hellinger distance between the corresponding distribution for the continuous time birth and death process and the distribution for the time-discretized version. Let me say that the Hellinger distance is very close to the Bhattacharya distance. The Hellinger distance is the unique divergence measure, which is a distance, and allows us to evaluate the similarity between two probability distributions. It was first defined in terms of the Hellinger integral and random Nikodin derivatives, and the expression for two discrete probability distributions is this expression, which is very nice to be computed for practical use. Well, our proposal is to determine the smallest number n of inspection times, verifying that the corresponding Hellinger distance between these two probability distribution is less than a predetermined value epsilon when epsilon is sufficiently small. Well, here I illustrate the Hellinger distance between the continuous descriptors and the descriptors associated with our proposal, the time-discretized version, the version when we observe the model at a sequence of inspection times. In a similar manner, we may compute the Hellinger distance between the continuous process and the discrete time, birth and death process of Allen. Well, in these cases, we are again considering the same parameters, n equals 20, gamma equals 1, and only one initially infective individual. I use green color in order to remark that in this region, we are dealing with a number m and a parameter beta for which the discrete time birth and death process of Allen and Burgin is not well defined. Nevertheless, you can see here the black color is similar to deal with a very good approximation. So for the proposal of Allen and Burgin, we have very good approximations, even if we choose parameters which are very close to the border of the region. Well, in our case, the time-discretized version is well defined regardless of the parameters. The selection of m, well, here, as you can see here, when m is small, well, we have an approximation which is not very good. But when we consider the region where the proposal of Allen and Burgin is well defined, the time-discretized version is similar but slightly worse. It is a surprise that the proposal of Allen and Burgin is always better in non-numerical samples when it's well defined. Well, this is a figure for the Hellinger distance when we consider the maximum number of individuals who are simultaneously infected, but the situation is very similar when we consider the minimum number of infective hosts during the interval 0 to prime. Well, let me say that in our talk, I have tried to present a probabilistic criterion that allows us to summarize the dynamics of the number of infected individuals in the original SIS epidemic model in terms of a sequence of numbers of infected individuals, in terms of a discrete time model. Well, we have considered the proposal of Allen and Burgin we can find in the literature. But we have built a second proposal, the time-discretized version, which is defined according to the observation of the continuous time model at a sequence of inspection times. Well, the key descriptor to define our probabilistic criterion is the Hellinger distance between two probability distributions. These probability distributions are associated with extreme values in the original process and extreme values in the time-discretized version of the original process. Well, for the two discrete time versions, they have a property in common. The dynamics of original process and the dynamics of these two discrete time versions are identical in terms of stationary distributions and the corresponding limiting distribution. With respect to the outbreak, the proposal of Allen and Burgin is able to say that we have a very good description on the average of the random length of an outbreak. Well, in our case, the property is that the random length of an outbreak in the time-discretized version is always stochastically larger than the random length of an outbreak in the original process. Well, the selection of the number n of expansion times in the interval 0 t prime to define the time-discretized version is associated with the use of the Hellinger distance. But anyhow, let me remark again that our intention was to develop a comparison and to establish when the proposal of Burgin is better than the time-discretized version, and where or what is the combination of parameters for which the discrete time version of Burgin is not well defined. So in such a case, the time-discretized version is the unique approximation that we consider that is good, or at least natural, to approximate the continuous time model. Well, here is a list of references. There are many references about discrete time models in Epidemic. The first paper is the paper where we can find the proposal of Allen and Burgin, but we can consider this second paper by Allen and Van den Driet, this paper by Gamboa and Maria Jesus Lopez Herrero, two of my collaborators at the Complutense University, which is very close to the paper of Allen and Burgin. This paper by Fabio Chalouf and Souza is very interesting because it's a unifying approach to the use of discrete and continuous SIS epidemic models, where here is the paper we are in these days finishing. And the last paper is related to the use of the Cayley-Hamilton approach, because in this paper by Krinik and Mortensen, we may find a solution for the time-dependent distribution of the birth and death process with catastrophes. So we felt that this use that Krinik and Mortensen are making in this paper, well, could be very helpful for us, and it was true. It was true. The problem can be solved by using the general approach they use in this case. Well, thank you for your attention.